Welcome back to our meeting, our weekly meeting. So now we are gonna have Maria Jose presentation. She's new in the group. She's a new face from Colombia, also like me. So she's gonna speak about Lepton Flavor Violation. So let's hear what she has to say to us.
No pressure. She represents the Colombian. Colombian Brazil. The Colombian face will be determined now.
It's too much pressure.
But no pressure.
Well, good afternoon, everyone, and welcome to my first talk. Today, I will be talking about Lepton Flavor Violation. I will start my presentation giving a contextualization and a little motivation about the topic. Then I will continue with going into the Lepton Flavor Violation. Then I will talk about some experimental present and future prospects of the topic, and I will finish with some conclusions. Well, I would like to start talking about the Standard Model. The Standard Model is a successful quantum field theory based on the gauge symmetry. It describes three of the four fundamental forces in the universe. The strong, weak, and electromagnetic interactions. The Standard Model is mainly divided into fermions having semi-integer spin and bosons having integer spin. The gauge bosons are the ones responsible of mediating the interactions among the fermions, while the Higgs boson is the one who gives masses to the rest of the fermions and to the rest of the bosons. Well, also, the Standard Model divides its fermionic content into three generations for both the quarks and the leptons. Well, even if the Standard Model is a really successful theory that can explain many phenomena in the universe, it is still an incomplete theory. And this is because, for example, it doesn't explain why do we have three generations. We still don't know what dark matter and dark energy are, and we still have the matter antimatter asymmetry problem. And also, the Standard Model doesn't introduce masses for the neutrinos, and the experimental evidence has shown that in fact they do have mass. So we don't know what is the magnitude of these masses. We don't know the nature of the neutrinos. I mean, if they are Dirac or Majorana particles. We don't know the hierarchy of the masses. And also, what concerns us today, introducing a mass term for the neutrinos generates Lepton flavor violation processes which have not been measured yet. Well, let's focus on the electroweak part of the Standard Model. Here we have its Lagrangian. First of all, we have some gauge terms, then we have some kinetic and interactions terms for the fermions. We have also the Higgs part that is responsible of giving masses to the neutrinos. And finally, we have the Yukawa couplings between the Higgs boson and the fermions. These couplings are the terms accounting for the masses and the mixings of the fermions. Well, if we want to study the flavor in the electroweak processes of the fermions, we need to take in mind that in general the Lagrangian is written in terms of flavor eigenstates. So we would need to make a unitary transformation to get it in terms of mass eigenstates. If we do this, for example, for the charge current for the lepton sector, we would find, taking in mind that the Standard Model doesn't give masses to neutrinos because it doesn't introduce right-handed files for the neutrino, we will see that this current will relate files of the same family. So we will get these fundamental purchases. However, if we perform the unitary transformation for the quark sector, and because a standard model gives masses to the quarks, we're going to find here the famous CKM matrix that will mix the flavor of the type up quarks with the flavor of the type down quark, giving rise to these fundamental vertices. Okay, I forgot to say something important here. I didn't put it here, but the neutral current here of this part of the Lagrangian doesn't mix the flavor among the files, so it preserves the flavor, right? That is for both quark sector and lepton sector. Well, let's talk a bit about neutrinos. And as I was mentioning at the beginning of the presentation, the standard model doesn't give masses to neutrinos because it doesn't introduce a right-handed partner for the neutrino. But the experimental evidence of the neutrino oscillations has shown that in fact they do have mass. So the flavor eigenstates of the neutrinos are linear combinations of the mass eigenstates. So this is completely analogous to the quark sector, and as we were talking about for the quark sector in the last slide, lepton flavor violation processes must exist. So this is completely analogous to the quark sector. Well, it seems that the neutrinos are one of the most mysterious particles in the universe. We don't know many things about them, and they seem to behave kind of different to the rest of the particles. For example, here I'm showing you a plot for the mass of the particles of the standard model. And well, we still don't measure the magnitude of the mass of neutrinos, but we have some upper limits. And they are near to 1 electron volt. So as you can see here, they are very orders of magnitude below the lightest particle, the electron. And this is really strange because if all the particles get masses through the same mechanism, there shouldn't be a reason to expect such a big difference. Well, and why are we talking about neutrinos? Well, the key point is that we need to find a model that successfully introduces masses for the neutrinos, and that explains correctly why their masses are so tiny, and also why do we have 3 generations. So the key point here is that these models should predict can predict some observables for the lepton flavor violation processes, observables that we can test using the experiments if we find the lepton flavor violation processes. And if we find them, we will be able to exclude or heavily constrain the models. So this will give us really crucial information of new physics beyond the standard model. And this is the key point of this search. Well, let's see what the minimal extended version of the standard model says us about the lepton flavor violation processes. This extended version is called minimal version because it's the simplest way of giving masses to neutrinos. In this model, we add right-handed partners for the neutrinos, and they transform as singlets under the gauge symmetry group. So we need to add this Yukawa term, completely analogous to the one we have with quarks, to the Lagrangian. And so this means that neutrinos will acquire mass through the Higgs mechanism, as all the fermions in the standard model do. Well, here we have a lepton flavor violation process in which a muon turns into a photon and an electron. And if we compute the branching radio of this process, we're going to get a really small number, 10 to minus 54. That's a really incredibly small number that unfortunately lies beyond any experimental scope, at least in the near future. So actually, this happens because in the minimal extended version of the standard model, the only source of lepton flavor violation is the mass of the neutrinos. So we can have larger branching radius in other more complex models because they can have more sources of lepton flavor violation. For example, here I'm showing you a plot showing the branching radio of this process. This is coming from the 331 model, a model which Professor Farinaldo was working in. And the branching radio depends on the mass of this file of here. I'm not going into the details of the model, it's just a parameter of it. So here we have two vertical lines representing two upper limits of the excluded region set by the colliders. Also, we have two horizontal lines representing the best current sensitivity achieved by the experiments and the projected sensitivity that they aim to achieve in the future. So this means that as we haven't measured a signal for the process, the region the region here up to this line is completely excluded. So what I want you to see here, what I want you to see here is that if the experiments are able to achieve these kind of sensitivities, they will fall into regions where these more complex models are expecting to see a signal. So this will help us to exclude or heavily constrain, or even to find to be able to find a signal of the processes. Here in this table, you can see the best present limits for some channels. Also, you can see the expected sensitivity that some experiments will be able to achieve in the near future. Well, in the history of the search of lepton flavor violation, the most popular particles have been the muons. And this is because they are relatively easy to produce in big amounts in the accelerators. Because of this, we have obtained the best bounds using muons. In this plot of here, I'm showing you the limits of some experiments for these three channels that the experiments have achieved over the time. So you can see here that we have a very significantly improvement over the time, and this represents, of course, a very positive prospect for the search of the lepton flavor violation in the future. Well, another popular particles in the search of the lepton flavor violation are the taus. And this is because they have a very big mass, so they can offer many more channels to investigate the lepton flavor violation. Here I'm showing you a plot with the upper limits of many channels, many decays of the taus. And as you can see, there are a lot of them. And these limits are set by these experiments of here. However, the taus have a very big disadvantage, and is that they are really unstable particles. They have a lifetime of around 10 to minus 13 seconds. That is seven orders of magnitude below the muon's lifetime. So because of this, we are not able to produce taus beams. However, besides all these difficulties that arise searching for these processes, the experiments have made a really good effort trying to search the processes, and are working now to improve the sensitivities for the next years. Well, because of the importance of because of the importance of finding these kind of processes, this search has become a really global search involving experiments of across the world, as you can see here, and each one works or is focused in different channels, different energy scales, and also different techniques. So as you can imagine, this represents a really positive and promising research file. Well, so to conclude, to finish our presentation, first, we see that the lepton flavor violation is a really powerful tool that will help us to exclude or heavily constrain beyond the standard model theories, and for that reason, it will give us crucial information about new physics beyond the standard model. Also, due to the global effort that it is done right now, we have really promising prospects for the lepton flavor violation in the near future. And as you can see here in this table, what I'm showing you is some the sensitivities that some experiments are expecting to achieve in the next years. So because of this, um, this is a really important research file, and it's because basically the experimental sensitivities are going to achieve regions that will allow us to exclude or to find these kind of processes that will give us relevant information about physics beyond the standard model.
So start for questions.
First, congrats, you learned a lot. The project was assigned. Well done. The future of Colombia.
Colombia, guys, Maria.
After Carlos.
So, pues, it's all of you who are working on Lepton Flavor Violation. So, if the mu3 gamma is subject to the strongest constraint, why do we care about mu3? Or inversely, so conversely. So mu3 is the amount of T2 minus 18 or so? I don't remember by heart. Do you remember?
No.
I think it's about T2 minus 18, 16 or so. So the bound of mu3 is around 10 to minus. Currently, I think it's about 10 to minus 12. Mu to T gamma is around 10 to minus 4.2, 10 to minus 13, right? Yeah? Is it?
I think I
Go back, you're gonna find that
This-
in your slide.
yes.
Yeah, that,
But for
one
the
more.
okay, see. Yes.
No. Yeah. So 4.2 10 to minus 13, mu to 3 10 to minus 12. See? I got it right.
Mhm.
All right. Okay? But the prospects from mu to 3 is 10 to minus 16. See?
Mm-hmm.
So this will go to 10 to minus 16. And this one will go to 10 to minus 14. Right? So my question is, so today, my first question is, this bond is stronger, right?
Mm-hmm.
So should I only care about mu3, mu2e gamma, and I should not worry about this one? Yes or no? David?
Then you should care about both because there's different portions of parameter space.
How? They're gonna cover different portion of parameter space if this one is stronger. The strongest is the strongest. Why should I care about a limit which is weaker? You have a limit and he has a limit. He has the strongest limit. The strongest. Why should I care about you? This limit is stronger. Why should I care about this limit?
Maybe it could be easier to produce the process in the colliders, in the experiments.
The expected limit to muon to 3 electrons is going to be greater for future experiments, right?
Okay, so now it's the same question. We will remain. See, in the future, let's say this one is the strongest. Now, why do I have to care in the future about this one? The question remains.
It could change. Both of them should be looked upon because they could change. We don't know what is the biggest limit every time. So you should check both.
Friends, today I shouldn't care about this first one. This one. Today.
I see.
Mm-hmm.
Is this true?
I don't know.
David? No? So, this is the experimental limit. Is one thing. The other thing is the theoretical value. So, in a given model, some models predict, my theory predicts, I say now is this experiment. Have X. In my HAP theory, my model, let's say my model predicts, that's the theory, okay? Predicts this one. My model. Is this allowed or not allowed? Maria? If my theory predicts this value, the experimental limit is this one. Is this value allowed or not?
What? I don't understand. What do you mean by allowed?
Is excluded by data or no?
Uh,
That's what the data says. It should be smaller. Smaller than this. And this should be smaller than minus 12. That's what you have. See? It's smaller.
I think it is
And
still.
my theory predicts this.
That is, I cannot see from
10 to
here.
minus 13.
Okay,
1, 3.
so I think it cannot exclude it yet. It is.
It's not excluded yet. Okay? Andres? Because minus 10 to minus 13, you can only prove 4 to minus 13. So it's still not there yet.
Mhm.
So my model survives. But maybe in my model, predicts this.
That is
The way
excluded.
it is.
See? So my theory predicts a model for this one which is consistent, but for this channel isn't. So that's why, despite this limit being weaker, I should care.
Mm.
Because this is experiment. This one is theory. And these values for the theory depends on the theory. Okay? That's why those limits, why I shouldn't care about all those limits. Because depending on your model, because look, this is 10 to minus 8, so it's super weak, right? Compared to minus 10 to 13, 5 orders of magnitude. Why should I care? Well, because depending on your model, maybe your model is already excluded by just this channel.
But in case terms of this hypothetical model, you can change the couplings, for example, for it to not be excluded or something like that?
Not necessarily, because they are related for this one. So let's see. Let's put Colombia to the test. Maria, draw the Feynman diagram of mu3. David, okay.
Sorry, guys.
I feel you.
Let's see. What is this in the middle?
The scale, I don't know.
Now you mean for this one?
For mu3.
For that
No, there's something wrong because you have the Fermion light cannot jump like this.
Yeah.
No,
No, it doesn't.
yeah, way far. No. So the mu 3 gamma is like this. Let's say this is a Z boson, this is a muon, photon, and muon. This would be, let's say, my new particle. I call it Maria, and electron. Okay? So my Maria is a vector force. The only difference between muon to E gamma to muon to 3E is that this guy goes, instead of being a photon, is Maria again that produce E plus E minus. Okay? Or you could say, now this is a photon. A photon produces E plus E minus. So you see, this part of the diagram, this one, actually this one, this whole part, is the same, right? For all of them. So I'm going to draw it again. Muon, let's say here, flag, some boson, muon, electron, and a photon. So this diagram is muon decaying to a photon and an electron. And now, instead of the photon being produced, this photon produces a pair of E plus E minus. And this diagram is the same as mu3 gamma. Right? It's the same. But now you have addition, 3. So the signal of muon to 3E is strongly related to mu to 2E gamma in this model. Okay? If I had a doubly charged scalar as in your model, then what you have is muon, it's called delta or S? S. S plus plus, S plus plus, plus or minus minus, depending on how you want to call it. Photon, this is a muon C, and this guy is in the light, or EC. And this photon can also go to E plus, E minus. Again, this channel is muon to E gamma. Or I put this muon E gamma. Muon to E gamma is this one, but if the photon produces E plus E minus, it's muon to 3. What is the key difference? When I'm talking about muon to E gamma, this photon here is a virtual photon. In the muon to E gamma, this photon is a real particle that produces the pair of E plus E minus. Okay? And this is fine. What is the mass of the muon? Hundreds of MeV. 200. Huh?
No, it's 200 times the mass of the electron, but it's 105 MeV. More or less.
105 MeV. 100 MeV. Half MeV. I have lots of energy. So this guy can have enough energy to produce 1 MeV in total. Easily. So this photon is real. This photon, when it's just muon to E gamma, is a virtual photon. Because what this represents does not represent a photon, it represents a magnetic field. Because this is a dipole moment. Dipole moment means coupling between a charged current, a charged particle, and the magnetic field. So this magnetic field is represented by this gamma. It's not a photon that's living. You don't detect this photon. Virtual photon, real photon. Okay? That's all. Okay, guys. I'm gonna give you some warnings, some news now in Portuguese.
I have to edit the stream.
I have to end this stream. Okay. Priscila, obrigado por participar, tá?
Ainda
Já
tá
tiver
ela
por aí?
Sim, ainda tá aí.
Ah, tá aí. Essa Priscila é nota 10 mesmo. Tá participando de tudo.
Sim. Well, well, thank you for coming, like and subscribe.